Alright, for lesson 4, kind of picking up where we left off yesterday. So quick reminder, if you didn't watch yesterday, make sure that you know the differences in notation. That's really important. A lot of true-false questions along those lines that matter for points. So anyway, today we're looking at a couple ideas. We're going to start working a little more with Venn diagrams. That's going to be kind of the heart of the rest of the chapter, or these special kind of diagrams. So first thing we're going to talk about today is the intersection of two sets. So again, if you think of kind of the intersection, that's where two things come together. So in this, we're looking for what they have in common. We typically associate that symbol with the word and. So that's kind of a something you want to be familiar with. So I would read this as either the intersection of A and B, or simply I would say the elements that are in A and B. And so if you think of it in those terms, where do these guys intersect with these guys, or what do they have in common? We can see that they both have a 4 in them. They both have an 8 in them. So those are the two things that those two sets both have in common. And so the intersection of A and B would be the elements 4 and 8. In terms of a Venn diagram over here, this area right here represents the A and B portion of the diagram. This is where they intersect. So if I were to list all the elements in A, so this is all of A right here, I'm going to put the 4 and 8 here because that's where it overlaps with set B. And then this is what we call A only. This is the things that are in A only but not in B. So I'm going to put the remaining elements 2, 6, and 10 into this part. So you'll notice within right here, within that circle contains everything that is in set A. These two things are also in set B, and these three things are in set A only, but not in B. But I still listed all 5 elements of A within set A. If I do the same thing for B, again you can see that 4 and 8 are going to go right here because I'm showing that those are in set A, or sorry, set B. But they are also a part of set A, so they go into the intersection portion. And then the remaining 3, 12, 16, and 20, can go into the B only section. So that's always a good way of taking a look at those. So moving on here to the second part. So right there we looked at the intersection of A and B. Now we are looking at the union of A and B. And the union is kind of mostly associated with the word or, because it's simply combining the two sets. It can be any element that's in A or any element that is in set B. They don't have to be in common. You are simply joining these two into one big happy family here, the union of A and B. So we're just combining the two sets. So we're going to list every element that is either in set A or in set B. So I got 1, 3, and 5. I got 5, 10, and 15. So they do have an overlap here of the element of 5. I'm not going to list it twice. I just list every element that is in either set. So I see a 1, I see a 3, I see a 5, I see a 10, and I see a 15. So that is the union of the two sets. So I listed every element that is in A or in B. Notice a little formula right here. This is something we work again with when it comes to time for probability. That if you were to take the number of elements that are in A or B, so that's right here, 1, 2, 3, 4, 5. The number of elements that are in A or in B is equal to the number of elements in A. So there were 3 elements in set A, plus the number of elements in B. There are 3 elements in set B, minus the number of elements that are in A and B. So the intersection of A and B, you'll notice that there was 1 element that they both had in common. And so notice that that creates our true equation that we have right here. So the number of elements that are in A or B is equal to the number of elements for A plus B minus whatever they have in common. And that would always give you a true equation right there. So moving down, the complement, so just another vocab word and another symbol. The complement is that symbol right here, and the complement we associate with the word not. So these are the things that are not a part of a certain set. So if you look right here, set B. So this is set B right here. So set B is referring to integers less than 5. So if I took a look at the integers less than 5, really important that we understand right here that this is the universal set. When you're given a universal set, this is the universe for this problem. So when it comes to listing the elements of set B, I can only look at the numbers that are in the universe for this set. So let me show that really quickly with a Venn diagram. So if you look right here, so this is the universe that we were given. So here's the universe. In set B, we're looking at integers less than 5. So for set B here, integers less than 5 is right here. So we would identify this as set B. So now when it comes time to saying, okay, let's list the elements that are not B, I'm simply going to list the elements that are in the universe that are not in set B. And so now I can see that 5, 7, 9, and 11 are the elements that are not in set B. But this is really important. You'll notice that I only listed the numbers that are in the universe for this problem. They have to be in the universal set, otherwise we don't even consider them. So that's really important that you understand that. So typically you're always given one of these for a problem, and then you're given something else. So whenever you're deciding how to respond to this, you always have to consider what's in the universal set for this problem. If you look at the last one here, so notice on this one that in this universe, in this universal set, I'm looking at all integers. So I have an infinite universal set right here because this is every integer under the sun. Negatives, positives, going from negative infinity to positive infinity. So that's my universe for this problem. So I can't even draw a Venn diagram for this because I can't list all the elements in the universe here. But look at this one. So if I said that set B is integers that are greater than or equal to 8, well then what is not in set B? Notice I can't list specifics for this because my universe is infinite. So it's not possible to list the specifics. So if it's not possible to list the specifics, you have to do it with an inequality. So for this last one, if I said that B is x's or integers that are greater than or equal to 8, well then what are the things that are not in B? So if x is greater than or equal to 8, then the things that are not in that set would be all the x's that are less than 8. So in this case, we're going to say all x's such that x is less than 8. And that's the only way to write that answer because I can't list the specifics because it's an infinite list. And so for that one, I have to respond with an inequality. Just a side note, we refer to this as set builder notation. This notation right here is set builder notation. So if you're ever asked to write your answer in set builder notation, that's what it would look like.